This is the beginning of Unit 4, and we're now going to look at integration using tables of integrals. All the techniques that you've learned are still valuable, and we're going to find that sometimes the techniques that we learned are actually even more efficient than what we're going to see in the tables, but there are other times when the tables will be extremely useful and will make integration a lot faster and more efficient. There are whole books written with tables of integrals. We're going to restrict ourselves to the tables that are in your book. It's actually, I think it's inside either your front cover or your back cover, depending on your edition. I've just torn mine out, so they look like this. And the tables of integrals themselves, when you have like a Proctored exam, a final or something, will be provided to you. You certainly aren't going to be memorizing these, 106 or 108 integrals that are on this table. But we're going to talk about how to use the tables in this section. There are two types of integrals in the table. We have direct integration formulas, and these are the ones where literally whatever the integral is, they simply tell you directly what the answer is going to be. Some of these you're going to recognize as ones that we already know. There's others that are not part of our little short table that we've been using, but are more complex. The second type of integrals are the reduction formulas. We've seen one of these. Remember the one with the powers of secant? We've seen these, and I told you there were more. Here's a whole section of reduction formulas that can be used as well. Notice your table is organized by types. You've got a section of basic integrals. These are mostly the ones that are in your other formula sheet. You've seen them all before. We've got trig integrals in a section here starting with number 30 and continuing on down to number 50. You've got your reduction formula specifically to trig integrals. And then you've got forms involving certain x squared minus a squareds and a squareds minus x squareds and so on. Forms involving ax plus b, exponential and trig functions together, exponential and log functions, and then some miscellaneous. So they're sort of organized in categories to help you know where to look for the formulas that you need. Nonetheless, there tends to be quite a bit of searching around. The ones that I'm going to do with you today, I'll help you find them, but as you get used to using your tables, you'll get more used to where to find the specific integrals that you need. So we're going to start with some that are just direct integration formulas. In our first example, we want the integral of arcsine x dx. And if we simply look for this one, sounds pretty basic. So I'm looking at my basics, and they do happen to call it inverse sine, but there it is. And we're simply going to copy down the answer, and it's as simple as that. So I have x inverse sine of x, or arcsine x, plus the square root of 1 minus x squared, plus c. I'm going to have you, when you do these and use a table, tell me which number you used from the table. So in this case, I used integral number 16. I'm going to document my work by saying, hey, look, I used number 16. And there we go. Number 2, tangent cubed x. Probably I should look in the trigonometry section for that. So let's see here. I am looking, and I'm noticing number 40 is exactly what I want, tangent cubed x. So there's my integral, and again, I'm just going to document by saying it's number 40, and then I'm going to copy out my answer. So number 40 tells me I get 1/2 tangent squared x minus the natural log of absolute value secant x plus c. Simple as that. All right, in example 3, dx over x squared minus 9. This is an x squared minus a squared form. And so there's a whole section here, integrals involving x squared minus a squared, that I'm looking at. And as I look through this section, I'm finding number 74 here. Looks like this, with an a value of 3. So number 74, putting in a equal 3, I'd have 1 over 6 times the natural log of x minus 3 over x plus 3 plus c. One thing to note when you're using the integral tables, the integral that you're using must match perfectly, other than perhaps a different letter, a different variable. Like if this had been a y or a u or a w, that would have been okay. But other than that, the integral that you're doing must match the form of the integral in the table exactly. If it doesn't, you may be able to use some algebra tricks or some U substitutions, things like that, to get it to a form that you'll be able to use the table for. And we'll see some of that examples like those coming up. All right, in example 4, x cubed sine squared 3x to the 4th. The first thing that jumps out at me when I look at this integral is there's a relatively obvious U substitution. If I let u be that inner function, the derivative would be 12x cubed, and I have an x cubed out here. So I think that might be a good start, at least, to this problem. Let's do a standard U substitution, with u being 3x to the 4th. du is 12x cubed dx, and so 1/12 du is equal to x cubed dx. I do have the x cubed dx, so that U substitution is going to work out just fine. And I have the integral of sine squared u and then I'll replace the x cubed dx with a 1/12 du. Okay. That leaves me with sine squared u. Now, we did study in the last chapter, the last unit, how to integrate things like that. But now that we have the tables, we should be able to take a shortcut. Let's see if we can find something in the trig integrals section that would help us out here. Trig integrals. And let's see, sine squared x looks like it's right over here at number 31. So I'm going to use number 31. And let's see, I have my 1/12. And other than the fact that the u is here, I'll have to plug a u in for the x. I'd have u over 2 minus sine 2u over 4 plus c. And that was number 31. Again, just documenting. All right, the integration is done. I just have to put back in what u is equal to. So let's see here. I'd have 1/24 u, which is 3x to the 4th, minus 1/48 times the sine of 2u, that would be 6x to the 4th, plus c, and then just minimal simplification. 3/24 is 1/8. Excuse me. All right, let's try another one. Looking at this next one, first thing I'm going to say is that 3 could easily enough be pulled outside my integral, so let me do that first. And then in the denominator, under that radical, I don't quite have x squared minus a squared, but I could probably get something that would have that form. So I'm kind of going for this general form, the x squared minus a squared form. But to get it, I'm going to have to play around with that denominator a little bit. I'm going to factor out the 4 and make that x squared minus 5/4. And then the square root of 4 is 2, so I'm just going to put a 2 in the denominator and pull it right out of the integral. All right, now I'm going to go to my list, and I'm going to see if I can find something that has this general form. I've got the x squared minus a squared idea going on here. And looking through there with the x squared on top of the radical, thinking, let's see, does it look like that one? Number 73, I believe. So let's use number 73. And let's see, my a squared is 5/4. So a would be the square root of 5/4. Or the square root of 5/2. Sorry, juggling papers here, trying to make sure you get to see everything. Let's do it like that. All right. So I've got the 3/2 outside the integral. And then looking at number 73 here, first thing I have is a squared over 2. So a squared would be 5/4 over the 2. And then I've got the natural log of x plus the square root of x squared minus a squared. So that would be x squared minus 5/4 under that radical, plus x over 2 times the square root of x squared minus a squared. So under that radical again, x squared minus 5/4, and then plus c. All right, we're going to clean that up just a little bit, and we're just about done with this one. Let's see here. This is really 5/8, right? I could bring this 2 up as a times 1/2. So multiplying this out, 3 times 1 times 5 would give me 15 over 2 times 2 times 4 is 16 times this natural log plus, I'll make that 3/4 x times the radical plus c. All right, let's keep on going. Sometimes we need to use some of the little tricks that we reminded ourselves of at the very beginning of Chapter 7. Remember those? Things like factoring, completing the square, multiplying by a form of 1, all those kinds of little tricks, long division, right? Things that we sometimes use and help us out when we're doing integrals. Sometimes we need to use those same tricks in combination with tables to help us do our integrals. And here's a good example. I've got this radical, and it's not just x squared minus a squared, right? That, or x squared plus a squared for that matter. That 4x messes me up. So I'm looking at that thinking, what if I complete the square? That's such a common thing to do when we've got a quadratic that's not factorable. Let's go ahead and try starting by completing the square. All right, let's see. That's a -2 squared would be a +4. And I'll compensate by subtracting 4 out there. So I have the square root of x minus 2 squared plus 4 dx. And this is looking a lot more promising. We've seen these before, and we usually just let u be what's inside here being squared. So let's do a quick little u substitution. We'll let u be x minus 2. du then is just the same as dx. So that becomes u squared plus 4. And again, dx is just the same as du. And now I've got that x squared or u squared plus a squared look. So let's see. I'm going to grab my table here. And if I go to, I guess actually it's up here, this section, where I've got a squared plus x squared, that's the type of problem I'm looking at. And in fact, the very first one here, number 76, looks pretty good, right? We have got our a squared would be the 4, so a is 2. And so I'm going to have, this says x over 2, for me that would be u over 2, times the square root of a squared plus x squared, for me that would be 4 plus u squared, plus a squared over 2, so 4 over 2, times the natural log of x, which for me is u, plus the square root of 4 plus u squared, plus c. So there's everything from our table. All that's left to do is simplify just a tiny bit and then replace all of the u's with x minus 2's. So this would be x minus 2 over 2, square root of 4 plus x minus 2 squared, plus 2 natural log of x minus 2 plus the square root of 1 plus x minus 2 squared plus c. And I will just mention, when we have our 4 plus the x minus 2 squareds, it happens a couple times, right? Remember, that really just came from this originally, after I completed the square on it. You could multiply it out again if you wanted to, x squared minus 4x plus 4, and you get right back to here again. So my final simplified form, I would probably write something like this. Let's make this a 1/2 x minus 2, and then just multiplying out what's back under that radical. It was really x squared minus 4x plus 8. Plus 2 ln x minus 2, and again under that radical, if I multiply it all out, I get back to this, x squared minus 4x plus 8 plus c. And that's probably how I would write my final answer. All right, example 7. I'm looking at this, and right now I'm thinking that you can take a look, but I'm not finding anything that looks very much like that. That x to the 8th power is really a problem. I don't have anything with an x to the 8th power anywhere in my table, or any way I can get that easily. So I'm going to use another one of our old tricks. In this problem, I'm going to multiply by a form of 1. Now again, this is a bit of creativity. It may not be the first thing that jumps out at you, but let me show you what I'm going to do, and I'm thinking you're going to be able to see why. I'm going to choose to multiply by x cubed over x cubed. The reason being, that's going to put an x to the fourth out here. And if I let u be my x to the fourth, that'll just be u squared, which is great. And then also the derivative of x to the fourth is 4x cubed, which I'm going to have up here. So the pieces are going to kind of fit together for me. And I'm thinking it's going to look okay if I do that. All right, let's give this a shot. Doing my integral, or excuse me, doing my multiplication gives me x cubed dx over x to the fourth times x to the eighth minus 5. And for the reasons that I just mentioned, I am going to let u be x to the fourth. That way the du is 4x cubed dx, and 1/4 du is x cubed dx. Okay. That works out great since I've got the x cubed dx right there. So I'm just going to go ahead and replace the top with a 1, and I'll replace that x cubed dx with my 1/4 du. The denominator x to the fourth is u. X to the eighth would just be u squared. And then I've got the minus 5. Okay. All right, I'm going to look for a x squared minus a squared type of form. So let's see, x squared minus a squareds with an extra x out in front here. Let's see if we can find that one. Let's see here. Looks to me like this looks like a lot like number 75. Right, of course, again, I've got u's instead of x's, but other than that, 75 pretty much looks like what I've got here. My a value is going to be the square root of 5. Oops, 75. So I would have 1 over 2, oh, first of all, let me put this 1/4, bring that down. And then I've got 1 over 2a squared. So 1 over 2 times a squared would be 5, times the natural log of x squared minus a squared. For me, that'll be u squared minus 5 over u squared, and then the plus c. Just a tiny bit to simplify, and we'll have this. Let's see, that's 8 times 5, 40. 1/40th. Natural log of u is x to the fourth, so u squared is x to the eighth minus 5 over x to the eighth plus c. And there we go. So again, we're seeing a couple of those old tricks. We saw the completing the square, we're seeing the multiply by a form of 1, things that we've seen before happening again. All right, one more sort of standard one, and then we'll look at a reduction formula or two. In example 8, I'm seeing a rational expression or an algebraic fraction where the degree of the top and the degree of the bottom are the same. We've seen before that typically long division is going to help us out here, so that's what I'm going to start with. Let's divide the denominator into the numerator. X cubed divided by x cubed is 1. That's x cubed plus 4x And if I subtract, I get 6x squared minus 4x plus 3 as my remainder. As long as the degree is smaller than the degree of the divisor, we're done dividing, we've got a remainder. So I have the integral of the quotient, 1 dx, plus the integral of the remainder, 6x squared minus 4x plus 3 over x cubed plus 4x dx. This part, of course, is very simple, just x. Then I want to talk about the second part. One option here would be to simply use partial fractions. I could go ahead and factor this denominator as x times x squared plus 4. It's got an irreducible quadratic, but we definitely know how to handle that. In actual fact, partial fractions, I personally think, is the easiest and most straightforward way to go on this one. However, it is possible to do this one using some tables, so I'm going to show you how to do that, and then you can make your own call as to whether you think the table method or going back to the partial fractions method would have been easier. In order to do this using a table method, here's what I'm going to do. I'm going to go ahead and I'm going to factor an x out of the denominator, and I'm going to think of this as 1 over x times 6x squared minus 4x plus 3, and the x is factored out of here, so this is now x squared plus 4. Once I've factored the x out, notice that again I've got the degree of the numerator and the denominator being the same. So I'm going to do long division again. X squared plus 4 divided into 6x squared minus 4x plus 3. Dividing here is going to give me 6. And when I multiply, 6x squared plus 24. I have to subtract. So my remainder is negative 4x minus 21. All right. Now keep in mind there was a 1 over x that multiplied this. So for the quotient, I'd have 1 over x times 6. And for the remainder, I would have 1 over x times negative 4x minus 21 over x squared plus 4. This one's now easy. 6 times the natural log of x. And for the second part, I'm actually going to break it up. I'm going to split up this fraction like we've often done. I'm going to say I would have one integral that's the negative 4x over the denominator, x times x squared plus 4. And then I'm going to have a second integral that's the negative 21 over x times x squared plus 4. Okay. So far we've used long division, and we've also used splitting up the fraction technique. We haven't used a table yet, but it's coming. All right. These x's can be divided out. And that's just, we've seen this one a few times, right? The 1 over x squared plus 4, that's just that inverse tangent or arctangent integral. It's one of our basic ones. This one right here. So let's do that part. I'll pull the negative 4 out. And then, let's see, on the table, this is number 13. And I have an a of 4. Excuse me, an a of 2, right? That's a squared. So that's going to give me 1 over 2 times the inverse or arctangent of x over 2. Here I'm going to pull out that negative 21 and just write this as 1 over x squared plus 4 dx. And that becomes the last one that I need to work with. All right, let's take a look and see if we can find an integral that's going to help us out there. Let's see, we've got an a squared plus x squared plus a squared, or a squared plus x squared. So I want to go ahead and look in that section. And I think all the way down here in number 85 looks like it'll do it, right? We've got the x out in front, and then the x squared plus a squared. Again, my a is 2. So let's do number 85 with an a of 2. So none of this changes, except maybe I could simplify just a little bit. That's going to be a minus 2 arctangent. And then I'd have negative 21 times this number 85. I think we've used this one before. 1 over 2a squared. A squared would be 4. Times the natural log of x squared over 4 plus x squared. Plus c. And my last step is just going to be to simplify that just slightly. There's not a lot to do. Come this far, we might as well make it look pretty, right? That would be minus 21/8 times that natural log. And there we go. Now again, partial fractions would have been an option. And you may, I know for me, I might come out here from thinking, oh, I think partial fractions might have actually been the quicker or easier way to go. But here's a way that we could have done it using tables. All right, we're going to finish out this section by taking a look at how to use the reduction formulas. And we've had some experience with these when we did the secant one, but here are going to be a couple of others. So my first example, I'd like to integrate x cubed e to the 3x. Now if I were doing this without the tables, I would be thinking integration by parts, but this is one of those I'd really have to go 3 times to knock this all the way down. Here I think it's going to be simpler to use the reduction formula. So going to my reduction formulas, let's see here. This one is actually in the exponential and log section. Let's see, I'm thinking it's looking like number 102 over here. I've got x to the n, e to the ax. So let me get that where you can see it. There we go. So we're going to use number 102. And right now I'm going to notice that my n is 3 and my a is also 3. So I get 1 over a be 1 over 3, x to the third e to the 3x, minus n over a, 3 over 3, integral of x to the n minus 1, so that's going to be x squared, e to the 3x dx. All right, I still have an integral here that I can't do directly. It's actually still of the form of number 102. Again, very typical with these reduction formulas that you have to use them more than once. So number 102 again. This time n is 2. A is still 3. And let's see, that's just 1, so I can get rid of those. So I've got my 1/3 x cubed e to the 3x minus, and here comes the reduction formula again. Starting with 1 over a, be 1 over 3, x squared e to the 3x, minus n over a, 2/3, integral of x to the n minus 1 is just x to the first, e to the 3x dx. All right, we're getting there. Let me just start by distributing, so I'd have a minus 1/3 x squared e to the 3x, and then that'll become a plus 2/3 times, and here we go again. I'm going to use that same reduction formula, only this time I'm going to have an n of 1 with my a still being 3. Power on the x is 1 this time. So 1 over a, 1/3 x to the first e to the 3x minus n over a, 1/3, integral of x to the n minus 1, that's just going to be x to the 0, which is 1. I'll write it out here, but don't really have to, right? And then e to the 3x dx. All right, finally something good happened here. X to the 0 is just 1. So that's just the integral of e to the 3x dx, and that I can do. So I'm finally going to get a final answer here. That'll be a plus 2/9 x e to the 3x and a minus 2/9. And then the integral of e to the 3x dx, I'm going to do that little mental U substitution. Integral of e to the 3x would be e to the 3x, but I would have had to have let u be 3x, and that would have caused a 1/3 on the du. Plus c, and the only thing that's really left to do would be to multiply those and get a 2/27. I'll let you rewrite that all if you want to, but I'm just going to leave it like that because I'm about out of space anyway. All right, so there's one example of a reduction formula. Example 2 is another one. I've got the integral of sine to the 4th over cosecant squared of x dx. And the first thing I'm going to notice is, since cosecant is the reciprocal of sine, I really could just rewrite this as sine to the 4th x. And I could bring that cosecant squared up and make it sine squared. Sine and cosecant are reciprocals of each other. So what I actually have is the integral of sine to the 6th of x dx. Now again, you'll remember in the last chapter, or last unit, we learned how to do these powers of sines and cosines, but those were pretty long, involved problems. And I'm hoping that we now have something in our table that's going to help us. So I'm looking for trigonometric integrals again. And let's see here. With reduction formulas, since that's the stuff I told you we were doing. Here they are. And it looks like, actually over here, we've got sine to the n power here in number 52. So let's see what we can do with that. If I use number 52 with an n of 6, I'm going to get negative 1/6 sine to the 5th of x cosine x plus n minus 1 over n, that would be 5 over 6, integral of sine to the n minus 2, that would be sine to the 4th of x dx. Good start. Sine to the 4th is going to be that same formula. Again, with these reduction formulas, so often we have to use them more than once. So I'm going to do number 52 again, this time with an n of 4. All right, so 5 6 times the reduction formula here. Back up to here again, we'd have negative 1/4 sine to the 3rd of x cosine x plus, that'll be a 3 over 4, integral of sine to the 4 minus 2, or sine squared, of x dx. So, write down what I've got here. That's going to be a negative 5/24. And that's going to be a positive 15/24. Guess I could have reduced that, but I think there'll be one more step. And then I've got the integral of sine squared x dx. Now I could do my reduction formula one more time, but I think that exact one was actually in the table earlier under the trig forms. So if I go back and look at my trigonometric integrals, let's see if we can find that one. Yeah, there it is. It's number 31, right? Perfect, and I don't have to do any more work. So I'm going to go ahead and say, in order to do this one, I'm just going to use number 31. And that's x over 2 minus sine 2x over 4. And then my plus c for the whole thing. All right, one more line. Let's go ahead and get this looking all good. Let's see, 15/24 is actually what? If you divide by 3 top and bottom, that's actually 5/8. So that's going to become 5/16 x minus 5/32 sine 2x plus c. All right, so those are the reduction formulas. And that actually brings us to the end of section 7.6.